and computer design actually. And I'm going to briefly talk about, because since you know multiplexers, decoders, they're all combinational circuits, the basic fundamental combinational circuits. And now you learned about counters and registers, so which means you are now capable of designing more complex circuits. And I picked up this years ago as one of the complex circuits that we can design, insert into the curriculum of this class. Apparently, there might have been other designs that might be part of this class, but I picked this one on purpose. The reason being, there's a computer architecture class that follows this EE203, Digital System Design, next semester. Since the basic motivation behind computer architecture, I think I think it's safe to say that we spent about 6 to 7 weeks just focusing on the CPU, architecture, the microprocessor architecture in computer architecture class. That's why I picked this one, so that we could have some more space. Then we got now 2 weeks to cover the details of a simple computer. When I say computer, I'm not specifically talking about the entire computer. I'm specifically talking about the CPU, the central processing unit, and its design, because that's the main brains of all the management activity, and everything taken care of by this simple computer components. Other components are a bit more dumber, because you just have to send simple control signals to them to control them, and then you schedule their timing, etc. So the manager of the entire computer is the CPU, the microprocessor. That's why we'll be focusing on them for the rest of the class. Okay. Before we start, do you have any questions about anything about the past lectures? No? Okay. Let me just then move to the next slide. Okay, so I'm going to start with the definition of instruction set structure. I think I'm going to use the board as well, so let me just open the lights. Oops. Wrong one. Okay, here we go. Okay, so I'm going to use, although seldomly, use the board, so that's why. Let me open the lights. So I'm going to start with the definition. The definition goes as the name implies, as instruction set architecture. I'm going to call it ISA from now on. It's the acronym for that particular definition. This is the lowest level, the specification of a computer's appearance to a programmer. You have written a lot of programs, I assume, when you take Java classes, C classes. But you are actually interfacing yourself with compiler, right? So you don't know what's happening in the compiler. Compiler takes your code, translates it, modifies it, does a lot of stuff, and then it goes to an assembler, and then assembler combines everything because you may have some shared libraries, right? So those functions are also integrated into your code. And now your code becomes all these ones and zeros, right? Some of those ones and zeros are data itself, and some of them are control signals. So now you're going to see that, for instance, one of the things that you have to consider when you're trying to send commands to the hardware, you have to specifically design your words. It's like a language. Instruction set architecture is just a language. You have to first devise your language to communicate with the hardware before you start. You may say, oh, we already learned about the language. What is it? If clauses, for loops. Those are not languages. Okay? It's a language, but it's a very high level language. Those for loops and if clauses, all these conditional statements, these are all common to any programming language, right? What I'm talking about here is the language you specifically communicate with the hardware. If you pick a hardware, for example, x86, okay, is Intel architecture, for example, then there is a specific language to communicate with this device. That's called the ISA, instruction set architecture, okay? And when I say instruction set architecture, it's not hardware, okay? It's not software either. It is something that is just between the hardware and software, okay, that helps you communicate with the hardware and software. And that's what we're not going to learn the details of ISA because that's the part of computer architecture. Okay. However, I'm going to show you, in order to talk about the hardware that does the intended job, such as addition, XOR, other different types of instructions, I have to define instruction. I have to define instruction set architecture. And I have to define a simple architecture for you so that you can go ahead and implement it using Logisim or one of your favorite software packages, such as Multisim. Okay? So to come to that point, I have to define those terms, which are going to be essential in the next couple of slides. And one of them, and I think the most important, is the instruction set architecture. Okay? Okay, so once the ISA is given to you, then you are free to go ahead and implement your hardware. Okay? You can design your hardware any way you want. However, you have to be compliant with the syntax or the semantics that are indicated by ISA. Okay, so ISA would tell you your language, how to speak to the hardware. But you can use all the hardware tricks, okay, to reduce the temperature or to reduce the power consumption of your hardware. Whatever you want to do with your tricks, you can still do them as long as you stick to the semantics, okay, dictated by your instruction set architecture. What does that mean? This is kind of a high-level description, so let me just crack it down for you. ISA is going to have a set of words, okay? For example, add or XOR. Okay, those simple types of language. Before you speak, you have to first learn about words. When you go back to your, times of childhood, you may remember or may not remember. Sometimes you don't even know how to call an object because you don't know the name of that object. In order to construct languages, okay, and have more deeper understanding of objects around you, you have to start naming them. Before you name, you cannot have a language, you cannot have a sentence. That's exactly how we're going to do it, okay? We're going to first define the words, so we can use those words to create languages, which are going to be your programs. And those languages or programs will tell the computer to do a specific job. And hardware will understand that language because you as a programmer has got a contract with the hardware designer through ISA, Instruction Set Architecture, which is your language, okay? So, we will talk more about the ISA later on as I speak. We will probably take architecture class and learn more about them. But here is the overall picture of how the hardware looks like. Okay, there's this data storage, as you always have in any digital circuit, data processing units, and control units. Okay, data processing meaning that you have an input and output, mostly combinational devices. And they're going to be processing as fast as they can, and they start, producing outputs, and those outputs have to be stored. And then those data here must be an input to the data processing unit, and then it has to be stored again. Okay? This is kind of, as you see, some architecture based on stored programs. Right? You can store programs here, you can store data here, you can store anything you like. Okay? But this processing unit keeps receiving data and sending data. Receiving data and sending data. Okay? What is the control unit doing? Well, this control unit, of course, is going to have to be reading something from the data storage, such as instructions. It has to produce those control signals, such as multiplexers, selected. Okay, those are control signals. Those control signals has to feed the data processing unit, so the processing unit will know what to do. Otherwise, the data processing unit is just a combinational circuit. It's just a dumb circuit. However, the control unit will tell the data processing unit what to do. Okay? But what are those? Those are words. Those are sentences we were talking about, right? So your program that you stored, such as Java program, is stored in that data storage. And then there are those system-level software that translates your Java program to lower-level languages. Okay, what are they? Well, they are assembly code, for example. And those assembly codes also get translated into ones and zeros, right? So those, what you see if you open your storage, okay, what you're going to see is just a bunch of ones and zeros. But when you define a format to them, which is ISA, That would mean a language. If you know the mapping between ones and zeros and your words, you can just combine them and read the sentence, okay? Which is going to be meaningful for your program or for your architecture, okay? So the control unit has to know those commands. What are the commands? Like XOR, add, subtract, whatever whatever you want to do with those, with your program. Okay, the control unit now gets translated, get those programs translated into ones and zeros, such that data processing unit will work in the way that it's supposed to work. Okay. Okay. This is just general overview of what we're going to see. So now I'm migrating to the hardware part of the world. Okay. We still have a lot to say about the software level, such as the system level programs, the compiler designer, assembler designer, and how they are translating programs into those ones and zeros. Though that actually requires another class. So here I'm going to now gradually go to the hardware level, which is the below ISA level. Okay, so let me just remind you those. We actually have gone through that layering approach in the beginning of the class. You may remember. Okay, so this was ISA, and below that you have on top of that ISA you have system level software. What are they? Maybe operating systems, right? Or drivers, compilers, for example. Or assemblers. They have to know the ISA, the language. Okay? For example, Windows. How the Windows on Earth would be able to control your hardware, right? This is hardware. In fact, these are gates, right? This is gate level. Below that, you also have transistor level, right? Transistors. And physics. We're mostly interested in the ISA and gate level, right? So we are here. We're interested in these two layers. So those operating system drivers, compilers, assemblers, they need to know the ISA, the language. Okay? If they don't know the language, how could they even possibly be in communication with the hardware, right? The gates. Okay? So that's why I'm going to now talk about, I'm going to give you an example ISA, an example set of language words that describes your architecture. Okay? Then we're going to move to the gate level. How are we going to implement the ISA? The implementation here is not unique, by the way. Okay? Once you set the ISA, and that's exactly what most people do in the world, by the way. AMD, Intel, they come together. They actually have, particularly, they may have some, crosstalks. They may sometimes have a, they sit down on a table and figure out what common properties they require from a product. Those talks are actually very, very common. And they come up with a specific architecture. They may add their own later on, but they have some common set of instructions they agree on. Then they go ahead to their labs and then design the hardware. Those design may not be really the same. Actually, they're quite different. Because one design might be, for example, targeted for a mobile device application. And the other might be targeted for a high-performance computing application. Okay? So depending on the application, your design will be different. However, the ISAs will be common, will be the same for everybody. Because now, when you want to write a program, you know the ISA. I mean, when you want to write, when you are a programmer, I'm not specifically saying you're a Java programmer or C programmer. You are a compiler writer. You are an assembler writer. Okay, you're an operating system designer. Okay, these are the low-level programming. Okay, so that's why I'm referring to. You're a programmer. That means you're basically one layer above the ISA. Okay, applications are actually stays very, very top. Application. Somebody writes an application for Apple. Well, he's right here. They've got no idea about what's happening in those lower layers. Okay? Because, I mean, that's the beauty of abstraction. You have all these, blocks. They're separated from each other, so you don't need to know all these layers. Otherwise, you wouldn't be able to write an application anyway. okay? Because it's too complex to go, below those levels. Okay, now we'll talk about gates. Okay, we'll focus on here. Okay, most of the time. Okay, so as you can see in this slide, simple computer design can be decomposed in two electronic circuits. One of them is data pads. These are used for data manipulations that will actually contain registers, ALU, and other control interfaces. The other one, control units, that is used to control, the data pads. That includes control logic for data pad, and it can be implemented in two different ways. One of them is programmable, called microcoded control circuit, or non-programmable, which we call hardwired control. Okay? So this is the overall picture that you see. Data pad on the right-hand side, control unit on the left-hand side. Control unit accepts control inputs, and of course pushes out control outputs if need be. Data pad accepts control signals from the control unit, and it sometimes pushes out some status signals, such as overflow, for example. Okay? So for example, the data pad is supposed to do some addition or multiplication using 8 bits. However, your number, the outcome of your multiplication, is bigger than, it's a big number that cannot be represented using 8 bits. That means data pad has to send a status signal to the control unit, oh, there's something wrong, you've got to do something about it. Okay? So that is the main brains here. But this is who is doing the job. Okay? So data pad also accepts data inputs. Apparently, for example, A plus B equals C, right? So what is A? What is B? This has to go into the data pad. And of course, the C, the outcome of the operation, has to go out, which is the data output, right? Question? Mm-hmm. Yep.
So the data pad in the previous slide goes to the data processors section, right?
Data pad and control unit, these two actually the data processing unit. We're basically now analyzing the entire data processing cycle. Okay? So both of them belongs to the data processing. Okay? So we're processing data, but how are we processing the data? We have to have a storage, which is now inside the data pad, which you shall say in a minute. We will have registers to store information. And control units can be a sequential or combinational, or maybe a mixture of them, both. But it's going to send control signals to the data pad, so the data pad will know what to do. Okay? So we will probably have hundreds of switches. You can think of this as follows. You have a vessel, you have a huge, big, maybe water irrigation system that you're sending water from one point to another point. But those, that water pump will probably push a lot of water to, to send water to different fields. It's not a single field, but a different fields. That means it's going to be a branching out, okay, as it moves along. Some of the switches are closed, some of them are open, right? So if you'd like to, for example, send water to a specific field, you have to open that switch and close the rest of them, right? So that's exactly what's happening here. If you'd like to do addition operation, you open that switch, so the control at that specific point in that data pad is going to execute the addition. The rest of the hardware is not going to do anything, okay, at that specific moment. In the next clock cycle, for example, then you allow other stuff to do, other stuff to be handled by the data pad, by opening some of the switches and closing the other switches, okay? Those switches will be what the control unit sending those control signals, right? Those control signals will go to those switches, and when it's 0, that means it's switched off. When it is 1, it's going to be switched on, okay?
So the control signals are like the commands, right?
Not like that, because control signals will be produced from the commands. When you send the command, control signal sees the command and will open some of the necessary switches and close some of the rest of them. And we will see that. Okay? The commands will be like instructions. Those instructions will be translated into control words, and those control words will constitute your control signals. Okay? And most of the time, for example, your instruction size will be 16 bits all the time. But control words could be any length. 30, 40, 50, depending on how complex your data path is. Okay? This translation is the challenge, by the way. For example, you may want to set, for example, you want to just support 50 different instructions, then you can just go ahead and do the hardware control, which I'm going to talk about it in more detail later on. However, that hardwired control, for example, is not very flexible. When you want to add an extra instruction, oh, I forgot to add division to my instruction set. Well, yeah, you can do it, but you have to start over. You have to go to the beginning and start your design from zero. Okay? Why? Because hardwired control doesn't allow you to flexibly insert another instruction into a set, and then all of a sudden your control units will be also applicable to that specific instruction. That's not possible. Hardwired control, for example, had that disadvantage. That's why people sometimes use microcoder control, where you have sequential circuit elements, such as registers, to record those control words to those registers, so then you read them off from the register. But the disadvantage would be, of course, slowing down the performance. Again, you will have a performance hit here because now you have sequential circuit elements. Hardware control is purely combinational, so it's very, very fast. Okay? Anyway, we'll come to discuss them all later on. Let me show you a Datapad example. It's pretty simple Datapad. But don't be scared of the complexity here. It's pretty actually neat and simple. As we go through them, you will understand what I mean by that. So we have, for the Datapad, has also smaller subblocks like register file. Register file is a pure storage element. It has got registers, you see, and some combination logic that does not do any computation actually. There's no computation in the register. It just basically, we have all these AND gates because we would like to enable some of the registers and disable the other, right? It's just a switch analogy, remember? So we actually use this load enable to connect them everything into the AND gates. When you actually select a destination meaning that the following simple arithmetic, A plus B, send that to C. Okay, consider this simple arithmetic. Okay? We have A and B, and C. C is your destination. A and B are operands because they are getting into the operation. That's why we call them operands. So when you look at this simple picture, you see there's a destination select with 2 bits, which means you have 4 registers. That's why you need the 2 bits, right? Remember the decoder? It basically enables only one of those outputs to be 1, the rest of them are 0. So that means only one of those registers could be enabled. That's why you have a load enable here. If it's 1, then all these AND gates will be activated. It's just like transferring whatever they see in the input to the output. So when load enable is 1, and you send this address, okay, to each one of them, whichever one of these intended, okay, whatever the C stays. For example, if this C stays in R0, R0 being the top register, then this decoder will push a 1 in this 0 wire. The rest of them are 0, 0, 0, right? So which will make those AND gates all should pass 0, 0, and 0, except the top one, because the top one will receive a 1 here, and the load enable is also 1. That means this load is 1, therefore R0 will be enabled for write. Okay? So that R0 is enabled for write. The rest of them are not enabled for write. So when you push some number, for example, this, and you see this wire goes on top of the R0? That is your data. And this. Data is connected to R0, but not only R0, R1, R2, and R3 as well. They're all connected to the same data. That might be confusing for some students, by the way. Well, I'm not writing the same data to all the registers. Yes, you're not writing it, the same data to all registers. It's just connected because you need them in case one of them is enabled, right? So you basically send the data, exact same data to all registers. However, the one that is enabled by this destination select is going to get the data. The rest of them are not going to get the data. Okay? Because this is the enabler. It enables the specific register to be written as specific data. The rest of them are not going to write that data inside these registers. Okay? Okay, so this is the right part. So on the right hand side, this is the left hand side. Sorry. Left-hand side. Right-hand side, you see, every one of those registers are connected to 2 muxes, right? So there are four of these registers. So 4 of them registers, for example, connected to the first mux, let's call it mux A, okay? And this is mux B, okay? They're both connected to here, to 2 muxes, and the output of these muxes go outside of the register file. Why are we having those muxes? Because I'm selecting the A and B, whatever they are located. Suppose, for example, A is located in R1, and B is located in R2. That means I have to enable R1 and R2. Well, by the way, all of these, you see they're all sending their data to the mux. But the one that passes through the mux is selected by A select and B selected, which are both 2 bits. Okay? So in order to put A, this data A, which is R1 by the way, stored in R1, that R1 onto this bus, for example, this bus. Therefore, I have to select, since it's on R1, I have to send a 0, 1 here. If you send 0, 1, that means it's going to select R1, because R1 is connected to this one, and put that, whatever that data is, and bits of course, in here. These are not single bit, by the way. Both of every possible, you see all these wires? And there's this slash and on top of it, then is n. That means this is a bus. It's carrying n bits in parallel. Okay? It's not a single bit transferred. It's n bits, all of them together transferred. So you see that this is now getting this R1, whatever that R1 is, and this is now getting R2, right? R2 is also connected, you see? It's connected to these 2. So if you select 1, 0, if you set B to 1, 0, then that means this data here is going to be replicated onto this bus, and this bus now will have B on top. Okay? So this is A, you see this is B, okay? Now we basically selected our inputs. A and B now are selected, okay? And put on the appropriate buses for further processing, okay? But
so the right part is basically just for selecting A and B to be the written ones. Okay.
As I said, the register file don't have any computation. Okay. It does not do any computation. It selects appropriate inputs and it writes the appropriate output, which you shall see, after all these computations take place in this particular block, you will see there's an output here, and that output needs to be written somewhere. Okay? And that would be C. And that C will be written to R0 if you select load enable 1 and the destination select to be 1, 1. Is it 1, 1? No, 0, 0, because it's written to R0, right? So this is really 0, 0. Okay? Now, this is the register file. Have any questions about the register file? It just stores data, it sends inputs, it receives output. That's it. And writes that output, of course, to appropriate register. Okay? So there's no computation, nothing. And you can increase, of course, the number of registers. I'm just showing you the 4-register case. You can increase it to 8, 16. For example, the Intel architecture, the most recent modern technology, probably have 512 registers, okay, inside the CPU. And this is probably tends to increase every year, okay? I'm here at about 1,000, for example, 1,024, which is also a power of 2, by the way. 1,000 of 24 to be the number of registers in the next generation CPUs. The more number of registers in it, that means the more you can store information inside the CPU. What's the advantage of saving that much data inside the CPU? Well, speed, right? Because as you haven't seen yet, but in architecture you will, that there are other hierarchies in the storage, such as caches. L1 cache, L2 cache, L3 cache. And below that you have got solid state drives. Below that you've got hard disk drives. Below that you've got tape drives. Below that you have the DNA storage. As you go, it takes a day to get some information from a DNA device, okay? Because it's very, very, tape, for example, takes hours to get to the data, right? However, in caches, it takes only nanoseconds to access the data. Because cache is just right next to the CPU. In fact, right now, with the modern technology, in my time, for example, when I was, of your age, that was Pentium 3 450 megahertz. When I first get that CPU, actually my father bought one for me. I was very excited because it's one of the fastest CPUs of that time. And you know what? The caches weren't part of the CPU chip. It was outside. There was a chip here in the middle, and there are 2 caches right here, and then they packed it such in that way. And this chip does not have any caches. The registers, but no caches. Caches are right next to on right hand side and on left hand side. But now, for example, starting from Pentium 4s, and now with all these titanium, this most modern CPUs, there is no such a design. All these caches are not part of the CPU. CPU contains everything. Because at that time, the transistor sizes were big, humongous. Now we're talking about 2 nanometer, 3 nanometer transistors. It was 100,000 times bigger transistors of that time. That's why you cannot pack those caches. So it's about the miniaturization of technology. It gets smaller and smaller. Now the caches are part of the chip. So when you see a chip of that smaller size, you got caches, L1, L2, L3, a lot of caches. Actually, 70% of this chip is cache. Only the 30% is doing the useful job at this point. Okay? Anyway, we'll come to discuss more about that. There are a lot of exciting news going on the chip technology. Okay, now, next phase is the computation, right? Also, you see these registers, etc. This is the storage. Forget about it. It's just storing, writing, reading. Okay? How about this complicated job of doing some useful computation? So when you have some data here, there's this little mux that we put. Okay? Originally, this wasn't here, by the way. When you design your CPU, you don't have all these muxes. This is, after work, after the design, this is what you're seeing. Okay? Which actually supports a lot of instructions, not a single instruction. When you start, for example, designing a CPU, you will first start, designing a specific instruction, put all the components on the layout so that it can support, specific instruction. Then you think about how to improve your design by adding extra instructions, second instruction, third instruction, fourth instruction. So this the Datapad here supports a lot of instructions. That's why you've got a lot of muxes out, here and there. Okay? For example, this mux is here to support a specific instruction that helps you get some constant information, some constant data, such as constant number, from outside. Okay? For example, 3. You will see that there is a specific instruction for that. That's why they put a mux here. So you either select this data or this one. So let's come back to our instruction here. This is the instruction, by the way, the human readable instruction, okay, which we shall translate it into more computer version. But this is human readable instruction. This instruction says that I've got A and B stored on the register file. So why don't you just get them on the bus, because I'm going to operate them. I'm going to have an operation of addition on these 2 data. So therefore, you don't select constant in, you select this. Because you know that there is B on this. So that's why you select this, and B select is going to be 0. Right? It's going to send 0, so that is going to be now on this bus, which I call bus B. And this is still A, it's bus A. Okay, so they go now to function units. Okay? So now you have A and B ready to be operated on, but what are we want to operate on? Okay, what's the function we would like to apply to these 2 data points, A and B? Well, this is how you select this G select and H select. There are 2 units here. One of them is ALU, as you know. You already have designed this, Arithmetic Logic unit. You either have an arithmetic operation or a logic operation. This is shifter. You may or may not have implemented this before, but you know why we have a shifter in the function unit. Do you know why? I assume you know why. You don't? No? How can we use shifter to do some operation, some arithmetic operation? Say again? Latches. Latches are used for storing information. Shifter is not a sequential circuit element, it's computational.
Maybe two.
Oh, you mean shift register? No, this is a shifter. Like, you send information and you get the information, instantly. There's no register here. Okay? It's a combinational circuit element. Shift register can also be used for that purpose, by the way. If you want to design it, you can. But this This is the entire function unit is combinational. There is no sequential circuit, and why? Because we want it to be fast. Sequential circuit elements are bound to work with cycles, like the clock. If the period is long, that means you have to wait. But this function unit is all combinational. Why do we have to shift some binary number? For example, if I have 0, 1, 1, 0, 1, and I shift this to the right. For example, if I shift it to the right, then I'm going to have this 0 to shift to the second bit position, 1, and then another 1, and then 0, another 1. And this would be 0 probably, depending on what you push. Okay? So let's look at this data, rather than this. What happened to this data? Let me just put a 0 so that they have got the number of bits the same. So this is in binary domain, and it's also binary domain. What happened to this data going from here to here? They shifted one bit to the right. But what happened in the decimal domain? What's the decimal equivalent of this and this? What's the decimal number that corresponds to this binary number?
26.
26. Okay. How about this one?
13.
13. Okay. What's the relationship between that? Division. Division by 2. Yes. If you'd like to divide something by 2, you just shift it to the right. If you would like to multiply it by 2, you shift to the left. Okay? But a single shift creates a multiplication or a division by 2. If you'd like to multiply by 4, you shift to the left by 2, right? Or if you'd like to divide by 4, you shift to the right by 2. How about I'd like to multiply by 7? What do we do? This is not a power of 2. Power of 2. What should we do? But I can write this 4 plus 2 plus 1, right? Then why don't we just shift to the left by 2, and then shift to the left by 1, and then the original, put them to an addition, and then you get a multiplication by 7. Okay? Of course, it's going to take more time to do that compared to its multiplication by 2, multiplication by 4, division by 4. But the shifter can help you do such multiplications. So you don't need to worry about this extra, hardware to do a specific multiplication. Okay? Any questions about that? Shifters can be used to do multiplications and divisions. Of course, your division and multiplication, particularly the multiplication, is easy. But how about division by 7? Can this help? Unfortunately not. The shifting cannot help with division multiplication. Division is a complex operation. Okay? Multiplication is not that complex. Okay? So as you go into the details of implementing such simple arithmetic, now you can basically order the complexity of implementing addition, subtraction, which is the same actually now, multiplication, which you can obviously see is easier compared to the division. That's why in, for example, the modern architectures, multiplication takes less time compared to division. Okay, now you know why we have shifted, right? Okay, now you're going to actually introduce your own instructions later on, maybe at the end of the class, that will actually execute. You can execute the sum multiplication by 7 using this Datapad, okay, by sending appropriate control signals. You will be able to do that, don't worry about it, okay? Anyway, now we have arithmetic logic and shifter. So you have to select out of these. Arithmetic logic units support a lot of operations, which I'll show you the table in a minute, okay, if you bear with me. Addition, multiplication, incrementation, decrementation, okay? And shifter also supports right shift, left shift, or you stay still, you don't do anything, okay? So you got 2 bits to send to the shifter. Okay? Again, this is a specific design. What's your name, by the way? Yeah, your name. Emirhan. Emirhan may want to design the shifter using 3 bits because he has got these fantastic shift operations, like 3 shifts, or maybe 3 shift and then 1 back. Those type of, fancy operations can be implemented. I'm just showing you a specific implementation. Okay, don't get me wrong. You can change this design entirely. Okay, I'm just showing you an example. And in this example, shifter accepts 2 bits because I'm going to be happy if my hardware is able to shift to the right 1 bit, shift to the left 1 bit, and stay still. Okay, I'm fine with it because it's the simplest design ever. Okay? That's why I need 2 bits, because I just define 3 different options. In order to encode 3 different options, you need 2 bits. Okay? For the arithmetic logic unit, which you will see, there are different various types of arithmetic and logic operations. For example, XOR, AND, NAND, etc. This will actually help you with that. So we'll come to the design of these 2 in a minute. And you already have done the ALU, so I don't think you will have any trouble. And shifter is pretty easy because using multiplexers you can design a shifter pretty easily. So now you have got A, B. Let's come back to our example instruction. A plus B equals C. Right? We're trying to design this or execute this. So A and B here, so you have to select this function, whatever that 4 bits is that corresponds to addition. Okay, let's suppose 0011, which we'll learn in a minute, by the way, what that is for this particular architecture. This arithmetic unit, I suppose that you weren't coming today.
Yes.
But you did. Right? We have a recording on, so if you can go back to the video and check what we have discussed so far. Okay, so arithmetic logic ALU is going to take A and B, and then you're going to operate on them, okay, addition. And the result is going to be here, which is C. So C appeared for the first time at this particular wire. That's where you see the C for the first time. Okay? And you will see that C will be transferred to other buses, will go through some other muxes, and then finally this has to be written back to the appropriate register. That is R0, right? R0. But that's not where the C appears for the first time in the hardware. This is why am I emphasizing this? Because as you will see later on in the computer architecture, whenever something appears on a bus, that means that is useful. That can be usable. You can, if you would like to use C in anywhere else in your hardware, you can just put a wire here. You don't have to wait for the next clock cycle because that requires a clock cycle, right? Because registers actually are sequential circuit elements that requires a clock cycle to operate on them so that they can write the data, right? So this is, as you can see, this is obviously a single cycle computer. In a specific cycle, everything finishes or has to finish. Okay? In other words, if C does not appear here while you're writing the data to R0, okay, because of that mapping, that means wrong data is written. Can that happen? Yes, because there are some gate delays here, right? There's a gate delay. These muxes are all made of gate delays. ALU are made of gates, right? That means that requires some time to process information. If your period is very small, very, very small, that means your register is trying to write something, but that is something wrong because C didn't appear here, right? So it's a single cycle computer. That's why I'm saying this is a single cycle computer. Because at every clock cycle, the output has to be written to the appropriate destination register. Okay? Anyway, C appears here. These are all side information, okay? Don't worry too much about them at this point. We'll discuss them, more and more and more, maybe repeatedly, until you understand it. So now this is C, okay? There is nothing coming to the shifter because we didn't use shifter anyway. Anyway, I mean, this B actually appears in the input of the shifter, and if there is no control signal, as you can see, there is no control signal except this H, but that H selects an appropriate operation here. It's not enabling or disabling the shifter. So therefore, this B actually goes to the shifter. It pushes out some data, something that is not intended. But that is the input of this mux. Are we really bothered about this? No. Why? Because this C here must pass to the mux. That means I have to put this C outside of the mux. Can I do that? Yes, I can, by just introducing another control signal called MF select. If I set MF to 0, that means C will appear at the output of the mux. Right? Do I care what this is? I don't care about that. Okay? But why do we have mux then? Just, connect this wire to this. So you don't need mux. But then, I can't use shifter. Okay? If I wanna, this is a simple operation. Okay. But if you wanna implement this multiplication by 7 or multiplication by 2, then you have to use a shifter. Okay? In that case, you will turn this MF select to 1 rather than 0. And then, in that case, the shifter output now will be used and pushed onto the output of the mux. Okay? So it depends. What do you want to do? Depends on the instruction. Okay? Instruction meaning commands that we're sending. Anyway, now we have C here. Good, everybody happy, right? That C is actually at the outside of this function, so we get out of the function. We get what we wanted to do, addition. Okay, C is here, but there's one more thing we have to think about, which is, who is going to fill those registers anyway? Where is the A and B coming from? Right? I assumed A to be in R1. Okay, good job. And I assumed B to be in R2. Good job. But where they're coming from? Somebody has to write those data to R1 and R2 even before I operate on them, before I start this instruction. Who is writing? Again, CPU is writing. How? From where? Where the data is coming? Well, from the memory. You can think of this as a memory at this point. Okay? Don't worry about the caches and etc. We'll come to discuss them. But there is some external memory coming in. It's very fast. Assume it's very fast. Ideal. Infinite storage and fastest response time. Let's assume there is this ideal memory somewhere. Therefore, this is connected to memory so that we can introduce instructions such as load and store. These are also commands. If you want to store something or load something on the register file, then you have to get a data from this ideal memory and push it to this bus so that that bus can write to appropriate location. So even before this instruction is executed, you should have some load instructions here so that these A and B's are written to appropriate register locations so that you can operate on them. And that's exactly how CPUs work. CPUs transfer information first from the hard drive to solid state drive, then from the main memory, right? DRAMs, right? Remember DDR4, maybe familiar? Sound familiar? DDR4, and then from memory to caches, L3 cache, L2 cache, and L1 cache. This is the migration of data. That's the life cycle of data. Until it hits its L1, and then from L1, it's carried along to the registers, right, which are inside the CPU. Then you can operate on them using instructions such as this one. Okay? It's this life cycle of data. Go ahead.
So this happens before all of the stuff that we talked about right now, yes?
Yes. Yes. Well, you still use CPU, not this entire logic. This is not used. This is a data transfer operation. If this data now here is reflected on this bus, and this bus appropriate destination selection will tell you what to write, where to write. You first write the A here, and then B here, and then you stop. That's it, because you don't operate on them. Then the next instruction gets those data using those muxes, put them through arithmetic logic, compute the C, and then writes that C back to the appropriate destination register. Okay, so now you completed multiple instructions. Now you started actually executing instructions. That actually means your program is being executed by CPU. What I just described happens in a fraction of a nanosecond. Okay, to say the least. As the computer CPUs now, increase their speeds, that means that fraction I just talked about is going to be smaller and smaller. Okay, because we want faster, devices in our lives, right? Anybody objects to that? You want a slow device? We even change our iPhones when they slow down, right? Because they cannot deal with our data anymore. Their CPU is not capable enough to respond to our, pointing device, natural pointing device, our fingertips. They're unable to respond to our speeds. Why? Because of all these instructions are generated automatically, and they basically, cannot swallow that much data and that much instruction. Okay. Okay. You see, you're learning the intellectual, deep stuff, right? The rest of the classes are just, levels up. They're abstract according to this, because this is real. This is a real working machine. Okay. Anyway, C is here. So I select MD to be 0 so that C can be copied to this bus. Now C is everywhere, right? It's connected R0, R1, R2, and R3. Now it depends on which one of them I select using destination select. Okay? Those control signals are already determined, even before all this stuff that we talked about, this flow that I just described in a given period of time, okay, is executed. All these control signals are all there and they're waiting. They're just, 1, 1, for example, is already here. Or not 1, 1, sorry, 0, 0, right? That's the second mistake. And the same mistake I'm making. It has to be 0, 0, my memory. I think I'm aging. Okay, so that means I have to put 0, 0 here for that particular period of time because I always select R0. Okay? And the rest of them are the control signals here are 0, 0. This is 1, so you can write the C on the appropriate location also. So we actually complete one specific instruction, A plus B equals C, using this Datapad. You see, there is no control circuit here. We just assume a specific control bits, right? For example, MD select was 0, sorry. Whatever that G is, we'll learn about them later. But MF select was 0. NB select was 0. These are all selected. These are basically determined by another combination called, or maybe sequential sort, but some digital circuit, which is called control circuit. That gives you all these destination select, A select, B select, load enable. These are all determined by the control circuit. Okay? Okay, do you have any questions about this? So I'll actually go through some examples, which I just did together with you. But this is another specific example, which I use R1 plus R2 equals R0. This is exactly this one. You see how we are using? I put some, indicators on the same data path to show you what's happening. Okay? So we haven't used the entire hardware. You see, a partial portions of this hardware is used. For example, shifter is not used for this particular instruction. We have a name for them. It's called micro operation. The reason because these are small operations. That's why they call it micro operations or micro operations. Okay, that's just a name. Okay, I'm going to call them instructions, for example. I think it's much more meaningful. Okay, so you see, select A is 0, 1, select B is 1, 0. Oh, we set G to 0, 0, 1, 0 to do the addition because that turns out to be the addition operation. MF 0, MD 0, destination is 0, 0, load enable is 1. So that means when those are set, those control signals set, then we are able to, execute this micro operation or micro instruction. Okay, here are other macro operations. For instance, using the same circuit, other macro operations can be performed. MF equals 1 is shift operation. MB equals 1, apply a constant. If you want to apply a constant, then MB must be 1. You can initiate memory write by providing address and data load enable. You see that data is written here, right? Data is on this bus. However, how are you going to access information from the memory? Memory needs an address, right? This address you see is here, bus A, as an address out. Okay? And if you want to write something to memory, that may be also a possibility because you don't have space in your register file. You see there are 4 registers. And if you've got a lot of data, that means you have to write some of them to the memory. Then you have to send the data out. Okay? There's an address out and there's a data out. You may be wondering, where is this address is coming from? I thought that we're storing data here. No, you don't necessarily. You sometimes store data, sometimes you store address. Okay? Addresses can be used. Do you know the pointer concept? Yes. From C? Okay, that's exactly what it is. The pointers are actual addresses. They're not data, right? So that's exactly what's happening in the hardware. That's why actually people come up with the pointer idea. Because those registers do not necessarily store data. They sometimes store address. So when you want to point to something, that means you give the address, right? So that's exactly what's happening here. This address is coming from one of those registers. Okay. So you want to, for example, read something from the memory, then you have to have the address in one of those registers to push out. so that the memory sends you at that specific address the data to you, so that you can store that data to another register. Okay? Which is of course handled by another instruction. You cannot use addition instruction to do that specific operation. Okay?
Can I ask a question?
Question? Yes?
The control signals change depending on the design, right?
Control signals is part of the design, yes.
But they
If
will
you
be
come up with
different.
another data path, entirely different path, then you can define your own control signals. Okay? Nobody can object to that. Okay? As I said before, instructions, so you have to distinguish two important definitions here. One of them is instructions. Instructions are going to tell you what to do, like addition, or XOR, whatever. Okay? And these are going to be also binary sequences. I'm going to use, for example, let's say 16 bits to define an instruction like that. Okay? But that doesn't really mean I'm going to use 16 bits for the control. Control could be any number of bits. That depends on your design. When you get, for example, 16 bits, you're going to translate that 16 bits to, let's say, 30 bits. Each one of the bits in your control, I'm going to call it control word, by the way. Each one of the bits in the control word means something. It's either an input for the muxes, it's going to be either for the destination select, or select A, select B, load enable, or maybe some other control signals you introduce yourself, because you think it is useful for the CPU design. Okay?
And that length is determined by the control unit, right?
Yes. Your control unit determines that length. If, for example, I ask you to design a control unit, for example, what's your name? What was your name?
John.
John. John, for example, has its own design, and it uses 31 bits. And Emirhan comes up with another control signal, okay, control word, let's say, and it uses 28. That is possible, by the way. It's all about your own design. As I said, that's the beauty of being, independent as a hardware engineer. Once the instructions are known, this is ISA, language, then you can design that language in any way you like. Okay? You probably have your own concerns about, for a particular application, temperature, power consumption, or maybe you want to deal with less number of transistors, but maybe more power, because you don't care much about more power because you're targeting the high performance computing. Whatever the application is, but your design might be different, your control word might be different. Okay? Okay, let's see. Okay, so this is ALU. You actually have designed a single 1-bit ALU, remember? This is actually very close to that. There's this D logic that you're supposed to design so that you can use n-bit parallel adder. You see, n-bit parallel adder is kind of standard. We actually know how to design this. You know how to design it using Readable type. You can make it, a serial type using sequential logic, for example. Or to make it faster, you may use carry look ahead, type, right? So you can actually design this. You know this how to design it, or you don't even need to design it because this is available. In your CPU, please don't design your edit, please, because it's already available in your software. Okay? You can use any block you want. You don't need to design the details of your, if it's available. Okay? If it's not available, you have to do it. But otherwise, please don't even attempt, because some of you guys have done that in the previous labs, I assume, which is not a good practice, because that's going to consume your time. Okay? How about the ALU? Well, you have to design the ALU, because once you're given the n-bit parallel adders, then you have to devise this D logic so that you can have multiple operations. For example, in this case, I have, you see, A plus B, A plus 1, A plus A minus 1, A minus B, A minus 1, A, all this stuff has to be defined for this simple stuff. Because n-bit parallel adder can only do an addition, right? You cannot do all of them together. That means this B has to go through some transformation, as in the lab. Remember the lab come up with this ALU. So, gonna jump to this, because this is not what you haven't seen this before. That's why I would like to give some time, several minutes to discuss this. It's pretty easy, by the way. It's just a 4-bit left and right shift adder. As I said before, there are 3 operations here that are supported. First, you can shift left by 1 bit, shift right by 1 bit, or stay still. So you can see that the muxes are connected in such a way that, for example, if select is 0, 0, if it is 0, 0, C is 0, 0, that means B3 is here, B2 is here, B1 is here, and B0 is here. That's why I said it stays still. You don't really change it. Pass B unchanged. If it is 0, 1, that means IR, whatever that IR is, it's coming from the outside, is 0 or 1, is going to be your most significant bit. Now, how about here? Well, it's going to be B3, this is going to be B2, this is going to be B1. So that actually means it's shift right. Okay? Because it's, whatever this is coming from the left-hand side, is your most significant bit now. But this is now B3, H2 is B3, H1 is B2, and H0 is B1. Okay, so it's shifted to the right, one by one bit. How about 1, 0? If you select 1, 0, that means this is B2, B1, B0, and this is coming from the right-hand side. Okay, that means it's shift left by one bit. And what about 1, 1? Well, it's unused because I don't even need to define this because I've got only 3 operations. That's why I'm using 2 bits anyway. All right? But you can, if you would like to come up with some fancy shift operation, you can define 1, 1, so it's not going to go unused. Okay? Anyway, this is the simplest shifter possible. That's why but it can be designed using multiplexers, as you can see. Okay? This was logic shift. This is arithmetic shift. In arithmetic shift, things are different. Because as you know from sign numbers has 1 in the most significant bit position. If you would like to shift a signed number to right, okay, which is going to be a division by 2, by the way, if you divide a negative number by 2, would that change the sign? No. That means that 1 on the most significant bit position has to repeat itself. That's why we have this sign bit turning onto it. Okay? Because that 1 needs to be there. If it's a positive number, it's a 0, most significant. Then if you divide it by 2, it's going to be 0 anyway. That's why this 0 actually shifts onto it. In other words, that 0 goes here, but you produce another 0, okay, to put it on the most significant bit position so that the sign doesn't change. This is true for arithmetic shift because these are arithmetic numbers. Arithmetic numbers could be positive or negative, okay, and you have to keep the sign. That's why we have this shifting onto itself, okay. And similarly, you can use such a simple XOR logic, as you know, that we proved in our previous lectures, to check for the overflow or underflow. Because, as you know, if you divide by 2 or multiply by 2, you can either overflow the entire arithmetic, because it can, if you multiply 2, excessively, it will probably go beyond the number of possibilities you can present using n-bits. Okay? That's why we actually have to have an overflow check logic. And I expect you to have that overflow check logic in your CPU. Maybe not the underflow, but overflow that has to be there. Okay? And it's pretty simple. It's just a simple XOR, right? So please keep that in mind. Although this slide looks, complicated, it's not actually. It's just a simple shift, logic shift, extra shift here to keep the sign bits. Okay? Otherwise, the arithmetic logic will lose its, positivity or negativity, which is not desired. Okay? I mean, like, you guys are not looking very well, so just want to go back here. So if you got, for example, 4 bits, 1, 1, 0, 0, and it's a signed number. And if I push IR to be 0 here, and shift this to the right, that means this 0 will appear here, making the number positive. However, the previous binary number was 1, 1, 0, 0, was a negative number. Because we know, how do I know that? Because the most significant bit is 1. It's a signed number, meaning that's a negative number. So if you just erroneously put IR to 0, that would make this shifted version of the number a positive number, which is wrong. Okay? That's why I'm saying specifically that this shifter, for example, cannot be used as it's in pure form for arithmetic shift. Okay? But you can design a control logic for this particular pure shifter to make it both for logic shifts and appropriate both for arithmetic shifts as well. Okay? You can do that by just introducing a couple of muxes, right? So that you can say to this shifter, oh, take this IR, for example, from B3 if it's an arithmetic shift. If it is not, then take it from outside, you know. Such control logic can be added to this circuit and make it more complicated, but it would be more appropriate for multiple operations. Okay? There might be, for example, a circular shift operation, which you may define, which I can define in the exam, for example. Right? If that's the case, in the circular shift, you know, this bit has to go back to the most significant bit position. That means you have to have some output here connected to another mux here so that you can select the either correct version of the bit to be stored on this, I'm sorry, not stored, but pushed out as an output, you know, for this particular shift operation. It might be circular shift, logic shift, arithmetic shift, depending on which shift you want. You can select the mux, appropriate mux operation to turn it on and off. Okay? Okay. Okay, so here is how the register file looks like. You see, how many minutes do I have? Okay, we got 8 more, okay. 8 more minutes. So we got this register file that you have seen the internal design. E-data, writes, address information. They just, yeah, A and B, of course, these two address informations. Those A data and B data now goes in. You got this constant in, you know. This is function unit. Okay, so I don't need to really draw the details anymore. That's why I'm showing you this big level picture. And these are address out, data outs. And there's a max here to get information, data from the memory or from the function unit, and that data goes back to the register file to be written. Okay? This is the table for ALU. Okay? Apparently there are many function codes, not just too many, but about 16 of them. You can see, not maybe 15 of them. You can see that the function select that I showed you was 4 bits long. Okay? But I actually shown you this G. This FS, function select, will be a common determinant for the G and H. This H is for the select, shift select, right? This G is for the arithmetic ALU select. These two actually now combine because that makes it 6 bits. But it turns out that we don't need 6 bits. We just need 4 bits to describe these two because there is a simple transformation from FS to G and H. Okay? And this table shows you that because H is only used if there are either this type of transfer, B is transferred to F, right shift of B transferred to F, or left shift of transfer of B, left shift of B transferred to F. Okay? Anyway, I think I'll need more time to explain this, and I think you will need some time to digest the previous material. So I'll stop here. Okay? You got a question?
Yes.